So first of all, before introducing our next speaker, I wanted to make a quick announcement. So we have 7 people who were willing to give a poster presentation. So what I'm going to ask is if you can send me your slides by tonight so I can compile them. And we're going to organize the poster session, so 2 3-minute talks at the end of tomorrow morning session, so right before the lunch break, and tomorrow afternoon before the coffee break. So that's the only announcement I'm going to make now. And now I'm going to introduce our next speaker, Claudia Marastron. Claudia obtained her PhD from University of Bologna in Italy in 1998. Afterwards, she worked as a postdoctoral fellow in Munich at the Ludwig Maximilians University and the Max Planck Institute. After that, she obtained a very prestigious Marie Curie Fellowship to work at the Department of Astrophysics in the Oxford University. After that, she also obtained the Marie Curie Fellowship, the Marie Curie Excellence Team Grant Leader at the University of Portsmouth, where she got the reader job in astrophysics in 2009, and now she's a professor there. Claudia's research focuses mainly in theoretical astrophysics, evolutionary stellar population synthesis, models, and galaxy evolution. She has 177 publications, quite an impressive record, with over 17,000 citations. And I'm pretty sure that most of very famous paper from 2005, single author paper with more than 1,000 citations on evolutionary population synthesis models, analysis of the ingredients and application into high redshift galaxies. Claudia is also very involved in international consortia such as the Sloan Digital Sky Survey, the SDSS, the Dark Energy Survey, and also Euclid. So thank you very much for coming, and I will let you the scene now.
To have many citations, of course, this will count also people that criticize your work. But you don't mind, because the only thing that is important is that people know your work, because that's the thing. So thank you very much. We should study that fraction. So in fact, the aim of this lecture, and I would like to thank Laurie, Karin, and Thiago for this invitation, which I really like, is to get you through one of the main used tools in astrophysics, which is the theoretical modeling of galaxies, the spectral energy distribution and the mass-to-light ratio. This was already recognized in the 70s that you need to do this type of exercise because astronomical data don't tell you what are the physical properties of galaxies. You observe light, but you would like to know formation epochs, masses, chemical abundances. So you need a modeling on top of your data, and in this sense, there are very hardly ever pure observations in astronomy. You need to model on top of it, and this is the story of this model. In order to understand them, we need to go through stellar evolution. For some of you, this will be known knowledge already. For those of you, maybe new things. Feel free to interrupt me if something is completely obscure. And remember to ask a question. Remember that I didn't drink a coffee before this talk, because the organizer didn't provide. So I am in your same situation. Okay. Let me see if this works. So the aim of our modeling is to understand the big picture, not just one of the many galaxies in the sky. So we start from understanding what are the cosmic abundances. This is always our friend cosmologists pointing out that the vast majority of the universe is dark. And in fact, galaxies are mostly composed by this 4.6% of baryons. But there is a big advantage of it, that we can know the physics of this part, and we can use it to shed light on the unknown, which may be unknown or may even not exist. So the cosmic structure on the larger scale is in fact even easier to understand than when it comes to baryonic physics. This is a plot of in redshift space of what we call the cosmic tapestry. And if you zoom in, you will get the larger substructures that are galaxy clusters. In each of them, you can single out the galaxies, but every galaxy will be ultimately composed of stars. So when I started my PhD, one thing that my supervisor told me was that there's no hope you can understand galaxy or cosmology if you don't know the evolution of single stars. And in fact, I think this was the old school I still think is valid, and we will see why. So the other stronger point is that the dark ages, so when you don't have yet your first stars and galaxy formed, counted most for 100 million years from the Big Bang. What is known before is dark, and you, you can model it, but you can, it's very hard to constrain. The real constraint comes from the CMB, which is very constrained, and we use it to understand the rest. But for the most part of the universe, it is evolution of stars and galaxies. And so this is how this model would like to attack, to trace and to provide us a cosmic clock all over the universe. The other thing that is useful for this type of modeling and understanding is in which type of cosmological model we are working in. That's not subjected to the model of stellar population, as you will see, are completely independent of the cosmology. Stellar population don't care whether dark energy exists and whether it has that particular equation of state. But if you want to make an evolving galaxies, you need to, it's fun, let me put it this way, to assume that there is a cosmology. And the thing that was put forward in the 70s is what we know as the hierarchical universe, which obeys to the structure, to the law of aggregation of dark matter, which in particular is cold, because too hot dark matter violates other constraints of particle physics. So if you believe that we are embedded in dark matter and dark matter is cold, galaxies cannot but forming hierarchically. As you will see on Thursday when I give you my last things, the baryons are actually challenging this model from the deep. And you may be the student in the transition era in which we need to give up to this picture. In this picture, we know that this is a bottom-up formation where disks form first, or small dwarf galaxies, and they will coalesce following the aggregation of dark matter halos. All over the cosmic time, this is around the Big Bang, and this is our epoch, such that the straightforward prediction is that the biggest galaxy will form at the bottom of the scale. In order to verify or falsify this model, you certainly have to analyze galaxies, and as I will show you in particular, get their formation and evolution across the cosmos, and this is where the model enters. It was, however, recognized very early that galaxy formation is very complicated. While dark matter, as much as we even don't know whether dark matter exists, it only obeys to gravity, unless you put some relativistic correction. It's quite easy to make these dark matter halos, make it merge. All simulations agree on that. When you put the baryonic physics, that starts the problem. So there are a few things that we don't know from first principle. We don't know how to convert a mass of gas into stars. We don't have that equation. We don't know the exact feedbacks from stars. You actually know, if you know the distribution of stars, there is an incognita there, which is the mass distribution of them. And we certainly know very little about the AGN feedback, which became fashionable in 2006, after one of our papers, actually, so we'll show you that. And Darren Crotton, the next speaker, implemented in semi-analytic models. So these things are very complicated. So what do we know, however, for sure, is that when you have a star that can become a star and not a planet, you will have a certain mass of hydrogen and helium that burns and give you out energy following the Einstein equation. And the other thing that we know very well is the coefficient that you have to put in front of this. This is called the luminosity evolution. So whether your universe follow dark energy, exotic dark energy, dark matter, or whatever, any type of converted mass of hydrogen will give us out that energy. And that is at the basis of the models. One thing is the energy we will see, the other thing are the time scales. Stars and stellar populations evolve on time scales that are ruled by nuclear physics. In this sense, they are completely independent of cosmology. Note that cosmology does not give you a time scale. The only thing you do is to invert the Hubble constant and get the time out of which the universe had to expand in order to get that Hubble's constant as measured. But it is not a prediction of a cosmological model, it's an adjustable parameter. And that's why, and we will see towards the end of the lectures, there is a school of thought which would like to use the ages of galaxies as cosmic chronometers, because their formation should be pretty independent on the web in which they grow, up to a certain extent. So having done these notions, and now please follow me through the following. I'm going to recap for you basic processes of nuclear burning, metal production, and energy transfer. I will tell you what the stellar evolutionary model is, which are the building blocks of population model or galaxy model, and a few applications to stellar evolution. So what I said, the energy of stars is calculated with this equation, and this equation is not wrong. I say this because, actually, there is a part of this that is hidden. If gravity is modified, you can actually have deviation even from the energy that we predict from the sun. Let me show you why. The Einstein equation rules the production of energy in the interior of stars or in shell around the core, and that counterbalance pressure and gravity, which would make the star collapsing. This is called hydrostatic equilibrium, and I bet that you're studying this in school because we did it. I do it for my students, it should be the same. Now, here we have G, which is the gravitational constant. As you might have heard, over recent years, the frustration on not finding dark matter has motivated people to study modification of general relativity, which imply modifying gravity. So the first thing is, if we modify gravity, G might not be constant, and this would modify the energy of the sun. That's why we try to modify it on large scales. So all what I'm talking now work in simple general relativity Newtonian approximations. The other thing that we know very well is that there are essentially three reactions that the star can use to make light, and so your galaxy will shine because of this. There is the fusion of hydrogen into helium primarily, which can happen through two chains. Now I'm asking you a question. What is the sun doing now? Which one? I give you two options. Ha, you see? Yes, the first one, right. Why? Mm-hmm. There is a reason for that, and the reason is actually giving you how much energy you can extract from a star. No, so the answer has been right so far. We are missing why is the sun doing proton-proton chain and not the CNO cycle? So the sun is metal-rich, so it could use CNO, carbon, nitrogen, oxygen. The reason is the sun is too small. So it cannot contract over the temperature that would be useful for that. I hope this will not disturb us too often. I will tell you why. The sun is forced to do PP chain because it's small mass star, okay? And there is a mass cut for that. We'll come back to that. The other reaction that is useful is when you can transform helium into carbon, which happens after. The sun is not doing that. It will do this at some point. According to another reaction. Anything that fails to reach at least 1 million degrees in the interior is going to become a planet, a brown dwarf, or something that doesn't shine. Now, that's the reason why the sun is doing PP chain, because it can contract only to give you that temperature, and that temperature is enough, is sufficient to merge protons, but it's not enough for the CNO cycle. The CNO cycle requires stars that are more massive than 1.2 solar mass. When I will tell you about the cosmic chronometers, which is our way of dating structure in the universe, at some point there is a redshift, at which there is a transition between PP chain and CNO, which is very fascinating. And if you don't take into account that energy contribution, you will get the ages wrong. So the CNO is actually very powerful, but require larger temperature, and that's why only larger stars can do it. Now I have another question. Population 3 stars. You know what population 3 stars are? They are the hypothetical stars that formed shortly after the Big Bang. The first stars had 0 metals. So even, and that's the thing, even if they were very massive, they couldn't do CNO, not the first generation, because you need to build up the element before. And that gives us a certain energy that serves to reionize the universe at redshift 15, which is directly connected to this reaction, which is quite interesting. It's not sufficient, we know that. And finally, the 3 alpha reaction, which is very important because the cross-section of this reaction was determined by an astronomer, Fred Hoyle, a British astronomer, who was telling the particle physics that they were wrong. And that's the origin of our not amicable relation between astrophysics and particle physics. Why is this important? Because the epsilon of production of energy as a function of temperature is a steep function of temperature and changes enormously according to whether your star can do CNO or it has to go proton-proton. The reason why the James Space Webb Telescope can see high redshift galaxies at all is because you have massive stars burning CNO, and so you see the production of energy, and this can come to us. So these things are quite important because everything will go into your understanding of the next. When you know enough material of this theoretical framework to put together, you get 4 differential equations with a certain number, 7 variables, and a certain assumption regarding equation of states. And this is how people construct stellar evolution model that would tell you not just how the sun evolved. The sun is a very common star, but you need other type of stars in galaxies, and you do this type of modeling. This is what is called the stellar model or stellar evolutionary track. Essentially describe the physical properties that are essentially luminosity, temperature, and gravity, surface gravity of individual different masses. There has been a lot of work starting from the mid-60s by Iko Iben in where was he? He was a German emigrant, but he was active in the US, and Oppenheimer in Germany, Frascati in Italy, and Padova in Italy, followed by Geneva, Yale, and Victoria, have produced models that we all still use. And it's very interesting also to understand that there are different assumptions that make our models dependent on this initial stellar physics. But these are the main schools still active in the field. So a stellar model is something like that. This is the luminosity in log units. So where is the sun here? I'm looking at you because you're just in the first row. I don't want to put you on the spot. This is the luminosity in log units. So the sun will be here because it's normalized. So I go here, that's 1 solar mass. Okay? That's the temperature determined from the sun. That's the only calibrator we have. For all the rest, that is calculated theoretically. Sorry, guys. So all of these refer to stars of different initial mass. This is a 15 solar mass, 9, 5, 3, blah, 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 up to 0.25 solar mass. The lifetime of 0.25 solar mass is 14 giga-year, something like that. So these are stars that will allow us to see in the future. We actually don't know the abundance of it. We'll come to that. So you see that this is following the tracks of these stars. You will see at each time steps, which is implicitly there, how luminous and what temperature your star will have. To put you this in advance, when I do a galaxy model, I'll have to integrate the information from all the single stars that I presume will be in that galaxy in a way that follow this quite understood and well-based prescription. Generically, let us divide the regime in two. We have massive stars. Generally, are those that are more massive than 8 solar masses. They have lifetime between 1 and 30 million years. They end up as supernovae, and they leave us either black holes, stellar black holes. Have you heard about the gravitational wave detection? You know that these are stellar mass black holes. The cosmologists even didn't know they would exist before because of the known gap between stars and cosmology. Effectively, these are 36 and something else, 60 solar mass. Up to 100 solar mass of a star, you can produce a black hole that is 50 solar mass easily. You don't need any type of merging black hole. This is just to tell you that these things, how we divide the remnants became fashionable again, thanks to the enormous amount of money that is now being invested in gravitational wave detection. So you need to see which galaxy may contain these signals. When these stars evolve, they also give us very specific elements which we can use to trace the formation of galaxies. These in particular are alpha elements, oxygen, magnesium, and silicon. And we will see how to use that. Low mass stars have much longer lifetimes, like the sun. They end up in the things you study, Denise. Especially they give us white dwarf, and relevant to this chemical tagging, they release iron on a quite longer time scales. So, effectively, this is all what we need to have in order to understand the following, how to make integrated models. There are a few applications of stellar evolution that I would like to discuss before we go into the integrated models. The first thing why it's very useful is to age date Milky Way stars and clusters. This is called local cosmology. The Milky Way has a lot of very ancient stars, possibly no primordial population 3 stars. Who knows? First we thought they were very massive, now we are reducing the mass. With stellar model, because the stars are close by, or relatively close by, you can really age date them and trying to understand the formation epoch of the halo overall. Importantly, well before you, not you were born, I don't know, but you were active, it was thanks to the age dating of Milky Way stars that astronomers could reject an H naught that was substantially larger than 50. That was quite an impressive thing. In the universe before, globular clusters were formed before the universe, which of course was quite embarrassing. The second application, that is the one in which is exactly my field, is to integrate information to make evolutionary model for galaxies. But then you use it for cosmology, for defining standard candles, using supernovae type 1 for the Hubble diagram. You can use the calculation to constrain neutrinos, which are also candidates for dark matter, and so on and so forth. Let me briefly describe this, how the technique works, because I want to point out already in advance the model that I do, you don't apply to things in the Milky Way. Because in the Milky Way, you don't need to integrate because you resolve individual stars. But the moment you go out of the local group, you start to see nothing else than blobs, and those are your galaxies, and this is where you need integrated models. So if you are in the Milky Way, these are globular clusters, of which Raffaele will tell you a lot. How do you get the ages of these things? What I show here is a so-called color magnitude diagram. You can put other colors and other magnitudes, but what you see here is distribution of stars along particular sequence, which is what the topic of this lecture will be. And you want to fit these lines. And I will like, you are too young to appreciate, but when I started to study, the HST had not yet given so many data. These are fantastic data. I mean, here you can really fit one line. But before that, there were mass of data with huge error. Everything can pass through it. Now it's no longer the case. So you will agree with me that this particular globular cluster is indeed 12 plus minus whatever billion year. So in a universe which h not equal 100 without cosmological constant, the universe is 9 billion year. This date would not be accommodated. And this was the clue to actually revise h naught, would turn out to be incorrect. More than h naught was lambda. So these things are very important to give you an absolute scale of ages. And then to go and constrain cosmology and not the other way. This is an example of when you push this thing at redshift 6. What I'm showing here are data of a very distant galaxy. There, never ever you will have any hope to see the individual stars. So what people fit are stellar population models. The red is one comes from my calculation. The blue comes from another calculation. What is important here, you get time scales. So that's the main use of this model. When the resolution in stars is no longer possible, which is most of the universe, you have an integrated ACD and you start to do real cosmology. So now, from now on, I want to explain you how we calculate these things, how robust they are, the uncertainties they are affected, and how to use them. So the first things, let's take an aggregation of stars in our home, the Milky Way. This is one of the many clusters, I just like the picture. But what you can see here, there are red stars, there are white stars, there is even this blue star. Do you know what that is? I heard a whisper. This is an extreme horizontal branch star. So when you are at home, you can distinguish things, right? Then you compress and you see nothing. So what we want to do now is to understand all the details of the Hertzsprung-Russell diagram in order to make something that makes sense for our galaxy, because your distant galaxy at redshift 3.28 will have the same stars. So if you expand that cluster data in a diagram, you will see that you don't have a random distribution of points in a color versus luminosity. Let me say that this is a temperature indicator and this is a luminosity. Stars pile up in sequences. It was an interesting conference I attended in Pasadena 3 years ago, which match scientists with philosophers. And the philosophers immediately ask us, why don't you have any star here? Forget about this is contamination. So there are regions that are forbidden. You know why there are no stars here? There are also no stars there, actually. And you will see the white dwarf there. This is the so-called Hayashi track of the red giant branch. And you don't have any stable configuration of temperature and gravity that push you over there. So when people look at this diagram first, they notice that you don't have a uniform distribution, and you have many more stars in this region than in this region here. But on the other hand, those stars are far more luminous than the mass of stars there. This produced the basis of one of the key theorems that I use in my model, which is called the fuel consumption theorem, which Alvio Renzini postulated in 1982 to try to make a more analytical model of these things. This is what you have to remember now. So, in your galaxy at redshift 15, you will have main sequence, you will have a lot of other stuff. So we need now to exploit our knowledge and to make these things consistent with our knowledge at redshift 0. Let's start, you know the meaning of these acronyms, because I will, you know. In fact, there. I will explain them all. I don't use acronym unless they are as historical as the stellar evolutionary phases. I have to use it. But I'm going to clarify them all. The first phase is called the main sequence, which is the one where you find most stars. Now people call main sequence for galaxies as well. This came up a few years ago. We don't like that very much. But it is a way of saying that in certain sequences, the lifetime must be longer for whatever reason, or stable. So the main sequence luminosity is directly proportional to the initial mass. It's really directly proportional, and that's why it's a very clean region which we can model pretty well. Low mass stars will be cold and give you low luminosity. High mass stars will be much bluer and will give you much higher luminosity. That's very important to determine the ages of galaxies, as we will see. The other thing that is critical is which type of burning is occurring, which we said the CNO. The other important thing is that when typically you have a carbon, nitrogen, oxygen, you have a convective core instead of a radiative core. And then there is a physical thing that is called overshooting, which is an assumption we put in the tracks, which can change the lifetime of stars and change also the ages of galaxies. And I'll come back to that. These are high redshift galaxies from one of the many surveys of the HST. All of these things are massive main sequence stars. Just information. You see them in blobs because they have short lifetime. People were, I remember, who were impressed. Why do you see this is clumpy? This is evident for merging. Nonsense. Alma has shown that there is a halo. They are just born and die. And this is the fact that you see them illuminating is because the lifetime, I told you, is lower than 30 million years. Okay? And the reason why we can see galaxies at this very distant redshift is because of the steep relation with luminosity and mass that I just showed you. So it's important because when you analyze distant data, you need to know which type of population you are dealing with. So main sequence stars are very important at all redshift, but I would say critical in the high redshift universe. And that's why, also because they are so well behaved, we use them to indicate the age of a stellar population, which is something possibly you use a lot of time or you heard it, but what actually is the age of a stellar population? Because a stellar population, as we will see, may be made by a single burst, but if you take a spiral galaxy, it keeps cooking stars all over the cosmic time. So it is hard to define, we'll talk about that, but a good definition is that if you take the lifetime of the stars that is about finishing hydrogen in the center, so leaving the main sequence, that is at a very good approximation the age of the whole population. As I will show, more massive stars will have been dead already, and low mass stars, they are inertial on the main sequence, and they don't give you this indicator. So this was recognized to be the best age-sensitive part of the diagram. This is taken from the number at my webpage, but it's useful to look at and remind ourselves that 100 solar mass live 1 million years. Do you know when the dinosaurs left our planet? 62 million years ago. So it's longer than the age, than the lifetime of 100 solar mass stars, which is interesting. 60 million years is already pretty good. At 13, but then look at the relation, which is strongly nonlinear. At 13 solar mass, live 10 million years. 13, so I'm spanning order of magnitudes. In the meantime, all these stars are replenishing the universe with black holes. And then 1 gigayear is a 2 solar mass. 1 gigayear is redshift 3. Think about that. So at redshift 3, you will have already small mass stars. And then finally, you have 10 billion years roughly to that. Metallicity doesn't bother much, the turnoff. And you can understand why. Because the main sequence is a core burning location. So how much metal you actually have when you fuse hydrogen into helium, even with the help of the CNO, don't matter much. And this is the difference between the turn-off mass over a wide range of metallicity. There is a bit, but it's quite not sizable. Why is this important? This is one plot, it's an evolutionary plot. While you evolve these stars, you keep putting in your galaxies dead remnants We call it dead remnants. We mean white dwarf, neutron star, and black hole. You lose the massive stars, and you start enriching your galaxy. So this is the cycle of chemical evolution. And this depends on which masses you have and how fast they evolve with time, as we will see. So the turn of mass, which is the mass finishing hydrogen, is a key information for the evolution of galaxies. The next phase, so when the sun will have finished burning in the center, it can still resort to burn in a shell thing around the core. And this is the phase called the subgiant branch. As a bolometric contribution, it's just 6%. This is what I get out of my model. But it's a smooth transition phase. The envelope is not fully convective, so you have a range of temperatures. And this is quite a gentle phase to go through a transition until you go to the real realm or red giant branch. This I put for your knowledge. I don't know that it was not until 1991 that people really could demonstrate analytically why a star has to become a red giant, or how it does that become a red giant. Because before this paper, the actual radiation pressure from the envelope would disrupt the star. And this is the first one that put the equation such that your red giants are stable. This is very important because it's a very long-living that you find all over the redshift span in the most massive galaxies, and this is a red phase. So it will contribute to your integrated spectral energy distribution. It is important only in low mass stars because in order to have it long, you need to have a core in degenerate state. This is an important input of fundamental physics to astrophysics. You can write the equation of state degenerate, and then your low mass stars will live 1 billion years on the red giant branch. More massive stars go immediately in central helium burning. And this, I took this historical plot that showed this, so they are low quality, no HST. This is an open cluster of stars, and this is a globular cluster. Now, also to test how awake you are, which one would you think is the oldest? And also, why? But I'm also happy. Yes, please. Why? Why do you say so? No, thank you for answering. Go ahead. Tell me why do you say so? Yes, no, okay, brilliant. You gave the right answer, but visually, this is the oldest because here the stars stay a long time on the red giant branch. This plot that I admit is miserable show you that you have only few stars on the red giant branch, so cannot be that old. So you gave the right answer. But the plot is actually this one. You see that you have plenty of red giant branch stars here, while you have hardly any here. There is the regime of non-degenerate core, and so the star immediately goes away for some other things and devolve fast, while here the stars stay long, and that's why you see them. Good. Now, this is an image of a luminous red galaxy, the one we use in the Sloan Digital Sky Survey to trace a baryonic acoustic oscillation in cosmology. You see that this galaxy, besides being very massive, is nearly 10 to the 12 solar masses. The redshift is 0.7 possibly. It's full of red giant branch stars. We see that when we do the integrated model. Everything is old. It's like an old scaled-up globular cluster. Okay? So before we saw galaxy redshift 3 full of main sequence stars, here you have an inert galaxy, and how well you model these colors depends on how well you model this. I will always try to give you the evolutionary phase with which galaxy it applies to. Another thing that is quite important that regards the chemical evolution, the red giant branch is the location of the first convective dredge-up, which essentially is a dredge-up in the envelope that carries inward elements and especially fuel, and carry outwards a byproduct of the CNO cycle. And that's where people measure lines of giants and for abundances determination. One thing that turned out to be important for big galaxies is that the element magnesium is not involved in this mixing. So we can use it to trace the primordial abundances in galaxies. The one that is mixed up is when you have a soup and you dig it out, you bring up things that don't tell you about the initial condition of the soup. So this is quite important. The other thing for us doing models, because the RGB bump gets fresh fuel from the inside, stars live longer there, and you have a different SED that if you neglect that. After having finished the red giant branch, if they go there, the second obvious thing to burn is the helium burning with the 3 alpha process we said. This is actually a decently long phase of roughly 0.7 billion years, in which the star has actually also a tiny hydrogen burning shell. But, I mean, it is essentially the location in which helium is converted in carbon and carbon-oxygen in the core. And again, in stars that are small, the carbon-oxygen core becomes degenerate and sustain a type of giant, which I call the asymptotic giant branch, which can live longer in virtue of the fact that the core is essentially resistant to input of pressure and temperature. This is called the asymptotic giant branch, and is a very mysterious phase in which the star is dying, and is burning hydrogen and helium periodically in a series of pulsing regime that make it very bright and very difficult to model. Very interesting, and this was one clue, the very highly cited papers that you mentioned, it turned out to be very important in high-redshift galaxies, as observed with the Spitzer Space Telescope. So we'll see that, because these are very luminous and red stars. So this is in general for stars that are lower mass than 8 solar mass, the end point of their life. I mentioned this also, by the way, that during the asymptotic giant branch thermally pulsating, you have the second dredged up, so you mix the star again, and it's the only site, astrophysical site, in which you can form carbon stars. Carbon stars must form at the second dredge up on the TPAGB. So this make of them, this is what we argue in this paper, a fantastic age indicator for galaxies, if you can see the carbon absorption in the spectra of distant galaxy, because then you will know they have an age such that they have to develop AGB stars, which is roughly 1 billion years. And this turned out to be a quite important thing for the galaxy that Spitzer observed, although we need other instruments to resolve the molecules. This we haven't done yet, your generation. Now the star, the main thermal life of the star is over. The small mass stars will get rid of the envelope on very short time scales. So for example, when we do galaxy model, the dust and shrouded phase in this AGB can be safely neglected. The time scale is 4 years, and the star become very hot and become what we know as planetary nebula, whose lifetime is also short. In recent time, however, and we have been able to discuss it over lunch, it was recognized that the planetary nebula core, which is roughly 25,000 Kelvin, can excite H alpha, which is usually associated to star formation. So in big galaxies now, and I will show you a few plots of an ongoing work, there is a region, actually, let's say, a regime of H alpha emissions that are not at all associated to ongoing star formation, but they actually signalize the simple stellar evolution. Of course, if you get this mistaken, you are overestimating the star formation in galaxies. So that's why they actually caught also my interest, and now we put them in the models with quite interesting results. There are other type of exotic phases, some that are not very interesting to me, at least, as a modeler of big galaxies. Now, I want to tell you that because this was taken up by people like Conroy to make a big case of age confusion in galaxies. As globular cluster people know, it is observed in star cluster an extension of stars above the main sequence with more luminosity and bluer color. They are called blue stragglers. But I think people know what they are. They probably are merged binary stars of two main sequences, so they become more luminous because they are two. Now, you see that if you have a few of them, and imagine you integrate the information, so you don't have an HR diagram that you can distinguish, your population may become bluer just because of these merging binaries, but not because it's younger. Okay, so if you have these stragglers in a sizable population in a distant galaxy, you may confuse the age determination. The reason why I don't think this is a big issue is still the numbers are very little. So if you have a sizable 10 to the 11.5 galaxies, this perturbation is not going to make much. There are others instead that are more important that I want to mention because they are very important for big galaxies. They have been called AGB manqué or hot horizontal branch, meaning different things. But for what I want you to retain, these are hot stars that are old. Usually, a hot star is a big star, which of course is hot because of gravitational balance in the hydrostatic equilibrium. But assume you have peeled off layers out of your small mass stars, you go into the radial gradient of temperature, and you hot core, but not because the galaxy is young. One striking example of this is well-known phenomenon that is called the UV upturn in elliptical galaxies. Have you heard of it? This had a cosmological effect because, so these are spectra of elliptical. We have interpreted the data here with the models, but the data were taken before. Usual telescope would look at elliptical up to 3000, and you see a nicely falling spectrum. And so everyone agree elliptical are old because you don't have anything in the UV. And so what a surprise when Bernstein et al. 1984, pushing with the first IUE ultraviolet explorer, noticed that actually most elliptical, especially the most massive, and the bulge of M31 were actually coming up with the UV light. So people who like the hierarchical model said, yes, I told you elliptical are still forming stars in the local universe. But it was quickly recognized that this upturn are not a signature of star formation. Star formation will actually give you a pretty flat LCD, is what we show here. Because there is no reason to have one temperature, but it's a continuum of temperature. This is what we explain. So the best explanation we have is that actually the most massive galaxies will host the hot stars in their cores that give you a UV that have nothing to do with current star formation. In the cosmology side, on Thursday, I will show you our detection of the same effect at Rashi 0.6. So this is another important thing. Now we talk about the life, the light all these stars give us. Now, what about the dead remnants? Stars live and die, and they actually pile up masses in galaxies that 20 years ago were thought actually were the origin of dark matter. We talk over lunch about the Macho project. You know Machos. It's a bit of an unfortunate acronym, but it intends a small, massive, exactly. So the thing is, stars in this range will leave you a white dwarf with a range of masses, not the smallest one because they don't evolve. These guys will give us a neutron star of roughly 1.4 solar masses, so we can approximate there. And all of it will give us a black hole of a certain mass. And now, in my model, I assume that the mass of the black hole is half the mass of the initial star. But my colleagues in Padova take another relation that is less beneficial for the black hole, which is roughly a third. So if you have 100 solar mass evolving, you get at most a 30 solar mass black hole, where I get a larger one. You can ask me, why do you do it like that? This was based on discussion with my PhD supervisor at the time, Alvio Renzini, who told me that as much as we know nothing about the endpoint black hole, taking half is a sort of an Occam razor rule, but more sensible than others. This is what he said. Now, the reality may give us right because of this gravitational wave. We'll see. But what I wanted to say, when you do a global model, you have the living stars that give you the CD, but you have also these things that are called the remnants that actually give you the mass of the galaxies. And recent work have demonstrated how sensitive your mass-to-light ratio is to these recipes. Now, I'm getting towards a conclusion, and I hope the time is good, but you haven't yet flashed. So with the slide I've discussed, you know everything, such that tomorrow we do the integrated models. But let us first mention some uncertainties that are very important to understand also the limitation when you use these models, how much you can understand. When I started to do my PhD was 95, and these were the uncertainties, and they haven't changed. I mean, we know more, as I will show you, but the uncertainty have not changed, because these are basic uncertainty of stellar evolution that are actually very interesting to study. First things, in order to assess the extent of the convective envelope, we use an approximation called mixing length, which works very well, but it is calibrated on the sun, which is not even yet in the giant phase. You can extend this calibration to giants, it becomes more uncertain. What is important, and I will show you the results, changing assumption regarding the mixing length, change the temperature of your star, so change my integrated galaxy model. And so the spectrum also. So, I want to make sure that's good, okay, that's very good. So the mixing length will tweak the ACD, and I want to show you in which sense. Typically, the difference are noticed between my models and the Bruce-Wall and Shalom models, which adopt tracks calculated with a different mixing length. Second point, which is even more dramatic, is the extent of convective overshooting in the core, which I told you before, is actually giving more fuel in the star. So the star at given mass will live longer. So this, which is hard to model, affect even the lifetimes. And there was a paper a couple of years ago using my model and Bruce-Wall and Shalom model, which again have different overshooting, to assess the ages of galaxies up to redshift above 1. And at some point, you see the ages separating because of the overshooting, which only affect the highest mass stars. I think if we would solve this, we could even constrain the equation of dark energy, and I really want to keep you hot on that. I think it's the best, but it's difficult, so we need to understand how to do it. Of course, if you talk to me, I think I know which overshooting I would take. But let's keep it general. So these two are very important, but the actual drama for us is that the stars lose mass. And there is nothing we can do about. And mass loss is not known from first principle. Trash immediately papers that tell you they know the mass loss. It's nonsense, okay? The best they can do, as I did also in my 2005, is to calibrate some output versus data. And those output were as a function of mass loss, and you can have a handle of mass loss. Because mass loss is, it can even change from environment. It's difficult. It can also affect massive stars on the main sequence, but there the lifetime is short, so in a sense, it doesn't perturb your model too much, but it occurs at the tip of the red giant branch, so it changes the evolution on the horizontal branch and the temperature, and I will show you a practical example. And more dramatically, it ejects the envelope on the asymptotic giant branch. And the reason why my model were different from previous calculation is due to this assumption of mass loss. So let us remember, and I hope I'm coming here in 20 years to tell you that we have solved that, because we're going decades in this progress. But we have made progress. I don't want to appear too pessimistic. So the mixing length effect, I put out this plot in my papers, which show you stellar evolutionary tracks, luminosity versus temperature, from different calculations Cassisi is a modern rendition of the Frascati tracks. Girardi is a Brazilian, Leo Girardi, but he's in Padova, so he betrayed Brazil and he stayed in Padova. And he's calculating the Padova tracks with overshooting and a different mixing length. Yale, Y2 is stayed for the Yale isochrones, and Victoria are for the Canadian isochrones, specialized in low mass stars. What I point out in this paper is that take the solar metallicity, that's the red giant branch, then you take the solar metallicity in these two, and it's colder. That's temperature, right? It's bending and it's colder. In the same paper I show, if I calculate my population model with the two, in the second case I get a redder SED, but not because the population is older or more metal rich, because of the mixing length. So if you take the two model and apply to data, you would get different metallicities. And not because there is a different metal input, but it's because of the mixing length, which I found it interesting. The Apogee project in Sloan 4 is trying to calibrate this effect. And of course, as you notice, the effect becomes more pronounced at double solar metallicity, which, sadly, is the regime of the biggest galaxy, the elliptical galaxy, which are the one that I study most, and that are the cosmological probes. So let's see, we need to work more on taking a description on that. The other effect that I wanted to show you, this is a paper based by Francesco Ferraro in Bologna, which we've done many years ago to try to calibrate the extent of the overshooting, which can give different ages to galaxies. It's not just at things on stellar evolution that you swipe under the carpet. No, it really does. And what we have done here is to plot the luminosity of red giant branch stars over the helium clump, observed in globular cluster in the Magellanic Clouds as a function of their turn-off ages, with a generous error on their ages. And what you see here are two tracks of prediction, which I've calculated. They are based on evolutionary tracks with loads of overshooting and with no overshooting. And you see where the data lie. And there is not even within the generous error in the ages, you can reach to that. Now, the overshooting is actually a complicated one, because logically you would think that a convective core does not have a very regular border, and so it's going to erode the layers outside and bring hydrogen inside. So the problem is, I think the problem is that we don't know how to model it, because it's too complicated. My supervisor, who is a very pragmatic man, said always, but they don't know how to put it, so don't use it. You make a smaller error in ignoring it than in modeling incorrectly. I just say this is philosophy of science, you can take it or leave it. The fact is, when we plot these clusters, the separation is quite sizable. As I will show you, the cosmic chronometer are calculated with these two type of assumptions, so you actually can make some extrapolation there. I need to say that this was the size of overshooting accepted in tracks like Geneva or Padova in 2004. This extent has decreased by now. So these tracks are getting closer to these tracks. These tracks decided to put some overshooting to be politically correct, and so the things are getting closer. But we don't have one parameter to do. As a last plot, I show you this in globular cluster, which showed beautifully the effect of mass loss, which does not depend on age and does not depend on metallicity, just depend on mass loss. So if you have these things hidden in your big galaxies, you're going to get confused. This is a paper by Bellazzini et al., which feature 3 globular clusters, which have quite similar ages, actually. They have different metallicity, but that's not the point. So here you see the evolution of the phases I told you before. This is the horizontal branch, helium burning, here, here, and there. Okay? So clusters that are coeval This one is a completely red clump, so again, putting your galaxy becomes a red SED. This one is what we call intermediate. You have a fraction of fuel in the red, but a fraction in the blue. And this one is what we call blue plume, or even whatever. It's only blue. It suffers from so much mass loss for whatever reason. There is people call this second parameter, that the star escaped over there. Now, if you integrate that in a galaxy, that galaxy becomes quite blue. So, for example, in my models, I produce the model for different parameterization of this horizontal branch morphology. It's the people interpreting data should explore all of them, because effectively, these are just three innocent, this Milky Way, I think they should, but, I mean, there's nothing special about these clusters. And if you think a big galaxy with many more clusters, which morphology it will disclose, something we really don't know. Field stars may suffer the same syndrome. Some go blue, some go red, and this makes a mixture of unknown things. Okay, I hope this was fine. I'm concluding with the spectra. So far I've treated the energetics and the physics of the stars, which is not what we see. So let me use a cartoon. What we see is actually the reprocessing of light through the stellar atmosphere, and that gives us a spectra. And this is how we make models to then feature galaxies. So you know these things. So we have an energy that needs to be distributed. And instead of making entering model atmosphere theory, which is another complete separate study, which is very interesting, I just show you, observe the spectra from the work of the Milesh people, Patricia Sacke-Black and collaborator. Here you have, this is a beautiful black body, almost, a hot star with a sort of an intermediate gravity. Down here you have a dwarf star, cold, 3000, and very strong gravity. Here you have a star that is as cold, but the gravity is very small. This is a giant. Essentially, the other part of population synthesis is to associate energetic to this type of spectra. And it's hard, especially in these regimes of low temperature and high metallicity, because of the formation of complex molecules that are not included in most cases in the line list of model atmosphere. What you see here, these are observed spectra. As we will know, doing galaxies, especially these stars, become very fashionable indicator of the IMF in distant galaxies. So they got our interest so much that within the Sloan 4, now I'm showing a plot that is not in public and even proprietary data, but I don't mind, because you live stream. We have a project called MASTER, which means the Stellar Library of the MANGA project. MANGA is the IFU Galaxy Survey of the Sloan 4. What is the cool stuff? I'm showing one of the spectra. The spectrograph of this survey sampled this wavelength range without interruption. The old Sloan would stop possibly here. We have extended that to AGB stars and IMF indicators. So the hope is to get, in fact, a collection of real stars around the Milky Way. Hard part is to get the bulge, which is the most interesting of it, where we can have a grasp of the close near infrared to get the indicators that are very much debated in galaxy evolution at the moment. And I leave you with the last sentence. In order to attach that to population synthesis model, I need to know, theoretically, what is the temperature and the gravity and the metallicity of these stars. That you give me an observed stars, I do nothing with it, if I don't know where to put it in the theoretical HR diagram. I show you here two different calculations of the stellar parameter done by Jianping Chen, a postdoc in the States. Using a certain model atmosphere, she gets that these stars is 3,800, log G 1.67, and this metallicity. And this other group of people get a warmer star with a lower metallicity. This is true. So every time they tell you this is observed, there is nothing observed. Right? You have data, and you have to get out the parameters. What we are doing now, and this will be possibly beneficial for many people, we are going to use a series of model atmosphere of different kinds that people have not used maybe before, marks, and try to see how much all these parameters depend on your particular choice of this type of filtering, because this goes directly then into my models and people who use it to interpret. And I think I'm done. I don't know how long it took. Perfect, I like this. Yes, I don't have exercise. Sorry.
Hi, Claudia. Can you go back, or at least just mention the UV upturn? I was always a little confused by that, and you said, if I understood correctly, is this still emission from the photospheres? Is it not main sequence stars? What's the main explanation for this these days?
For these days, the UV upturn observationally, these are integrated spectra of elliptical, is observationally enough rise in the UV emission, okay, that initially could be attributed to young stars simply because it's UV, but this doesn't work. And so the most plausible explanation, the way we have done it here, is that you have old stars that have suffered from good mass loss, okay? Hence, they are small, but if you peel them, their layers, they become hot. Here, we have also calculated how much fuel consumption you need to make the exact upturn, for example, in M31. And it's really very small. So the chance of having these events in your massive galaxy, where there is high density of stars, maybe it's due to that. The reason is not known, I wanted to say, is non-zero. And what I'm going to show in a couple of days, as I said, is the same thing in the progenitor of this galaxy, Rashi.6. You start to look to see it. Because the UV upturn, you need the small mass stars, because you need to peel them with less effort. And so we have calculated roughly between Rashi.6 and 0.5, you should start to have them. Tom Brown, a guy who worked at the Hubble Space Telescope, have actually pursued the same study following using HST. They also conclude about the same redshift. So they can confuse. You see UV light, you think, oh, new star formation. Wait a second, because in the local universe, it could be that. That was the message. Well, this is the M31 bulge. This is a bulge. So I'm not sure it's the size. What seems to matter is the metallicity and the alpha enhancement and the age of the galaxy. M31 is not 10 to the 12, but it's a very old bulge. There are younger bulges. So no, it's not exactly, it's not the size. It doesn't seem to be the size. Yeah.
Hi, Claudia. In one slide, when you where you show 6 spectrum, you told me that you can tell about the gravity of the star just by the spectrum. How can you know that?
Well, I'm not sure I wanted to give you this message. Here you have a simple life because people have printed gravity. Possibly from there you don't see it. I would not be able,
No, I don't.
Cool dwarf and giants have similar absorption, but for example, the FEH band at 9000 is stronger in dwarf. The sodium one is much stronger in dwarf. The calcium triplet is stronger in giants. So you do the model atmosphere and understand how different they are. These values here come from comparing the observed spectrum to model atmosphere, which have included a certain gravity. You get the best fit, and that's how you get the gravity.
Okay, thank you.
Yeah.
Hello. In the beginning of the presentation, when you're talking about the CNO cycle and population 3, you said something about the reionization of the universe. I didn't get very well the
Yes.
relation.
Let me go back. Yeah, we need actually this plot. This is a nuclear physics plot in which you have the reaction rate energy output. So essentially how efficient your energy output is for given reaction, CNO and PP, as a function of the temperature in your plasma. Okay? Then we know from applying the hydrostatic equilibrium a certain star which temperature it has. But it shows you that, for example, increasing temperature, the CNO cycle gives you loads of energy, and that's why massive stars have a lot of luminosity that we see. The problem is, I became interested in these population 3 stars because they start to creep up in the primeval galaxies, because it's the first generation of stars. Because by definition they have zero metal, they could have not possibly immediately done a CNO, because they have still to make it. So the immediate second generation will do it. Will use the CNO byproduct of the evolution of these stars. Because the energy rate is so different, the first stars will emit less energy than we would have hoped to exploit them for reionization. That was my side remark. Reionization is complicated because at the present time, neither the number of dwarf galaxies nor the biggest galaxy that should be forming later are able to fully account for a faster reionization. I dropped my usual link to cosmology. That was the thing. The thing is, however, the immediate second generation of POP3, they can do the CNO. And simulation tell us that they are very massive. So if you follow this, they should have a lot of light. There is also this guy, just to let you know.
Hello.
Hello.
In that slide you showed some apogee data, the difference of the calculations. What do you think are the ingredients included in the difference? Because apogee does automated abundance analysis.
Yeah.
Could this be a factor or just a difference in the models that they use?
So it's a very good question. We are trying to actually, now let me see if I can do this. I could. This is important that you notice. It's exactly what we're working on that we would like to. So there is another nasty fact that entered the game, which I mentioned thanks to your question. Apogee is using to derive the parameter a very narrow region around the H band, so more near infrared only, okay? They use Mark's model as much as we do. I didn't show you in this slide, but I can show you the calculation offline. So in this sense, we need to understand whether it is the fact that they fit only a very narrow region, and that is driving the discrepancies. And we instead force the model to fit all over. And that's a compromise, right? The best fit will be different. It's a completely different strategy. Because we have stars in common, we are trying exactly to understand that. In order to inform the models, we are going to fit these mass stars with marks as the apogee people. Kuruk's classic. Plus we are using, although it's not my favorite, some observed color temperature relation that people have used in the past. Ideally, we want to minimize the things and get to one decent parameter. No, but this was, I should tell you that here, this one, I've reported, we are not going to use it. This is not based on model atmosphere. This is based on the temperature calibration of the Miles stellar library by the Spanish people, which is a bit of a hybrid, so we are not going to use it. So yes, these things are completely off, but we want to do something more consistent with what they have done. However, you note that model by Vasdekis and collaborator of others are based on this calibration, because this is the official Milesh calibration. I'm getting very nice questions, very to the point of numbers that I show. So cool.
You briefly talk about the formation of stellar black holes, yeah. But how galactic black holes are born?
How?
How galactic black holes in the center of the galaxies are born? Supermassive black holes.
Oh, sorry, yes,
Yeah.
sorry. For
Yeah.
Is the coffee waiting? Now, these are stellar mass black holes that I'm going to produce when I integrate my galaxy. Every dying stars will give you one of these stars. No way you go from there to the supermassive black hole.
Yeah.
I mean, people have done these studies. You would need a very high merging possibility to, it's not my phone. Sorry. It is quite clear that you cannot merge, unless you have supermassive population 3 stars, their mass is 10 to the 6 solar masses, half of it is half 10 to the 6, there you can go. But not with this type of stellar mass black hole, but this will give you gravitational waves, normal signal, actually, the one that you are most likely to detect because they are very many in number. And they can contribute to dark matter, I still think so. Good.
As I have time, at certain point you mentioned that magnesium was a very nice or important element because of not taking part of the mixing. And I would like to connect this with the mass, the different mass of the stars, in which it's more or less important. I just don't know, really don't know this.
I'm impressed by you are a very attentive audience. No, seriously. No, because you picked up on things I've said, so I need to explain it. That's very good. I tell you what the thing is. Magnesium turned out to be a tracer of the formation timescales of galaxies because it is ejected by supernovae type 2. So if you see a population enhanced in magnesium, that population had no time to get enhanced in iron, hence had to form on short timescales. This is the case for elliptical, and I'll come back to that. However, if magnesium would be a secondary element messed up by the dredge up, we could not use it as a primordial indicator. It has to be stay where it is. So it was good that evolutionary calculation by Renzini, Greggio, and the other guy that I don't remember, 1978, but I can give you the paper, show by calculating dredge ups that magnesium is not involved in that. So cool. So even in globular cluster Milky Way, you can measure magnesium. You know that it's quite primordial. Why, if you measure other elements, the carbon ratio, they are not. They are fine. They don't give you the same information. So my aim is to find out indicators for the formation timescales of galaxies from the knowledge on stars. I'll come back to that.
Hi, Claudia. I was curious, you said that you were looking into the effects, like the impact that it could have, just considering the H-alpha from planetary nebula as...
Yes.
What is that a
So we have
how
already
significant
published
is that
that.
in
Now I
what
tell
kind
you
of
what it
galaxy?
is, exactly. If you take a population of planetary nebula described by evolutionary tracks, I have used the one of Letizia Stanghellini, you will remember in Hawaii. It's difficult to do a planetary nebula track because there is the mass loss problem, okay? But these people are masters in this. She has calculated tracks, so I have merged it with my models and I've integrated how much heat or flux they will give us. And so in order to explain a linear region or region where you see H-alpha, but it's not that big, so it cannot be star formation. And using Sloan data and the manga data, we have shown that up to 3 angstrom, equivalent width in emission, you can explain it out completely with planetary nebula. And so we have correlated, this is published in Belfiore et al. 2016, which I can dig out. So let's say above that, I would have to stretch the evolutionary calculation uncomfortably. But below that, can explain out.
Can you hear me? Okay.
Yeah.
But you expect this to be more of an issue to, I don't know, host starburst galaxies? I mean, you don't expect this to be an issue?
No, it's not an issue. I mean, imagine planetary nebulae is the most obvious stellar byproduct that you can get. Every galaxy will have loads of them. So if we are able finally to account their contribution properly in an integrated model, then you can still use H alpha as a proxy of star formation, provided you subtract it. What you should do is to get the age of your galaxy. That will tell you how much your planetary contribute, because you need to have a pretty aged, a bit at least, some population. Subtract this away, the rest is star formation. But it's going to make possibly some indicator coming back better.
I have a question about overshooting. So you were mentioning that overshooting, depending on the one you're going to choose between your models or Bruswell and Charlot, can change the age, the determination of the age of the galaxy. And I was wondering if you see a difference in determination of the age at low and high redshift, and also if you see a difference between the type of galaxy, elliptical or late type.
Thank you for this question. So, by the way, these are all my models where I changed the track, exactly in order to single out the overshooting. I did mention that in Gustavo's model, he has as a standard input tracks with overshooting, so it will be on this side, but I don't want to annoy him. This is all my model changing tracks. I wanted exactly to pin down this effect. As I will show you, this is indeed redshift dependent, because overshooting is more dominant in more massive stars, obviously, because you need to have the overshooting core. Now you see why it was important. So what we found that the two tracks that start to diverge is around redshift 1. And they will diverge even more at higher redshift. I will show you this plot. It's part of the lectures. The type of galaxy is a good question. Usually, you want to have a population that contain well-behaved generation of stars, such that you can maximize the signal instead of getting new star formation. But even if new star formation will give you more massive stars, if at all the effect should be emphasized. But for the cosmic chronometers, you want galaxies that are the oldest and the more smoothly evolving, such that they follow the evolution of the universe. And these notoriously are elliptical galaxies, the most massive ones. Yeah. This is dangerous. No, but nothing happened. Thank you. Fantastic question. I really enjoyed it.
Thank you. Thank you very much.
Good. Thank you very much.